Hello and welcome to the Knowledge Forest. In this video I will be deriving Gauss's law in free space. So Gauss's law says that if you have charges and you have an electric field, or rather if you have an electric field, you can calculate the electric field at some point in space, and this electric field is actually equal to the area or the integral of the area dot product by the surface area, or integral of the electric field dot product by the area, and it is equal to the charge multiplied or divided by the permittivity of free space. So before we get to that conclusion, let us begin by the derivation. So suppose we have some charge that is in space, that is in free space, and I suppose, let's say, we have a surface that is enclosing the charge. So it could be a shell or something like that. But we don't want it to be a shell of a specific shape. Let's say it's an arbitrary shape, but this shape or space or sphere, arbitrary space surface is enclosing this charge. So what we're saying is we have a charge Q, and it is enclosed by some arbitrary surface. The charge that is enclosed within a surface, and what we have is that this charge is a positive charge. Therefore, as a positive charge, it radiates, or it produces, or the electric field is radiating from the charge itself. And since it's within a surface, we know that the electric field is symmetric about that specific charge in all directions. So let us say then, on the surface of this surface, or on the surface of this shape that we have, we then say that the electric field is going out of the surface, and the electric field is perpendicular to that point or that surface and is going out, and it's at a perpendicular angle. And then we define an area vector dA, which is also going out and is also perpendicular to the charge or to the surface as well. So there is a perpendicularity between the surface itself and the area vector. Okay, we say then we define a radius from the charge to that surface. We define it as R, and this R hat or R vector is equals to R in the R hat direction. So we see that the R hat direction is actually also perpendicular to the surface. Okay, now let us then say, okay, from this charge here to that point or to that surface, we define a rotating region, or a rotating, I suppose, field, or rotating vector which is rotating, or rather a vector which is creating some angle. So let us then say something like this. From our charge we define, so let me zoom into this becoming our charge all the way to the surface, and this is the surface part with the dA, with the area, then with the electric field, and of course our R hat, and this is R hat, so let's call it just R, so the radius. Now we're going to take this radius which is projecting, or which is coming from our charge Q, and we say it is sort of like rotating, therefore we create some sort of rotation. But we see that this rotation is at an angle. This angle here, which is of the rotating radius, is actually, we're going to call it omega. So let's call it omega. This is what's called the solid angle. So we're not going to really go into the definition of the solid angle as much. That is a mathematical term, just as all the rest of the mathematics we're going to be using in this derivation. So we're going to say there's a solid angle which is sort of like rotating from the charge to the surface, and we define it as that solid angle omega. Now we then say that for any surface, or for an arbitrary surface, the solid angle is actually equal to 4 pi. So this solid angle is equal to 4 pi for any arbitrary surface. Then, having defined these things, let us then say that electric field from the charge has got a flux. There's a flux, that is to say, there's a flux that's going in or going out with an amount of field lines which go through the surface. So let us define the flux. We're defining the flux to be this symbol for flux is equals to E, the electric field, dot dA. So we define it as an integral, a closed surface integral, E dot dA. So it's the number of field lines which are going through the surface. In this case, they are going out from the charge, therefore going out of the surface. Okay, having defined this, we know that the electric field of a charge can be defined, and we know it, and the equation for the electric field, I shall write it here, is equal to this. The electric field is equal to 1 over 4 pi, the permeability of free space times the charge over the radius, all that in the r hat direction. So this is the definition of the electric field. Now having that, we can substitute it back into our flux equation. Therefore we have the following, that the flux then is equal to that, and we substitute our E there, which becomes 1 over 4 pi permeability of free space. Let's put a Q on top there. So that's our Q, and the R hat direction dot dA, this over R squared. But we notice something. We have already defined what is called the solid angle, and that R hat over the D, or R hat dot dA over the R squared, is actually defining the solid angle. Because if you would like to look at the magnitude of R, it is going to be R squared, but over obviously the norm of the vector or the radius. That R there is actually equal to R is equal to some distance, or its magnitude that it actually has. So the value of R, which is equal to, I suppose, R squared, something like that, right? So we've got, if the magnitude vector of that vector is just simply R. But what you want to note is that with respect to that thing is the R hat direction, which is somewhat rotating around the area A over this radius. So that they should be defining our solid angle. Therefore, we see that in our integral, we shall introduce our solid angle, and then we have the following there. Since that's a dA, that means we have an elemental solid angle. Therefore, our flux then becomes equal to, well, let's take out the Q over 4 pi outside the integration. So we should then have Q over 4 pi permeability of free space, all that by the integral, which is also a closed surface of d that lambda, but we already know that it's actually 4 pi. Therefore, let's remove it from being a closed surface integral and simply define it as from 0 to 4 pi. And we see that when we do that integration, we end up simply having the following case, that this will become Q over 4 pi epsilon 0, 4 pi, and this cancels out. Therefore, we end up having then the following result, that E dot dA, which is this closed surface integral, E dot dA, E dot dA is actually equal to, and that's actually Q over the epsilon from permeability of free space, so the charge over the permeability of free space. This right here is Gauss's law in free space, and that's how you derive it in integral form. But this, we must know that it is only with respect to charge or point charges. So let us generalize this to more of a surface. We don't want to just deal with one charge. What if you want to consider a collection of charges? What if you want to consider a conductor? How then do we look at the electric field, and how can we derive Gauss's law for that? So to then generalize this equation, we imagine there is a number of charges, right? A number of Q's in that specific arbitrary shape that we had. Those number of charges, we're going to define what is called the volume charges, or we can say that we've got the volume charge density. We're going to say that the volume charge density, rho T, right, is actually equals to the number of charges Q per unit volume. So per unit, let's say tau. That's how we define it. But of course, we want to work in this case, initially we want to work with integral or elemental volume. So let's work with dq and d tau. So d tau in this case is the elemental volume. So that is to say we are going to isolate an elemental volume from there, which is something like this. Okay, that's a weird shape, but this is our d tau, an elemental volume that we are isolating from that arbitrary shape which we had initially. So that is now what is going to be our charge, but we understand something. We have a q there, so how about we then say that dq should then be the charge, the volume charge density, times the elemental volume. Then that is to say dq becomes that. So we are then going to have to integrate over all the number of charges in that elemental volume. So then this becomes the following case. We then have E dot dA then becomes dq, but we want of course the integral. So let's have 1 over E naught over the integral of dq dt, or that part here, which is our dq, right? Which then becomes rho t d tau. So that will give us an integral of all those number of charges which are concentrated in that shape that we have, our arbitrary shape. And from this, we can now think about doing some stuff, or we can actually think about working further with this. Okay, there is an identity, or there is a theorem which exists, and this theorem is called the divergence theorem. So the divergence theorem says if you have a surface which encloses a volume, you can write the following. We can change this because we know it's a surface. In this case, we had initially a surface. So let's call the surface maybe S prime. Therefore, the integrals are going to be the integrals over S prime, right? This will be over S prime, S prime, S prime, S prime, and of course, this becomes S prime, right? The same thing can be said about that, which is now, of course, another S prime. But we already have a surface S prime which encloses a d tau. And because of that, we can use the divergence theorem. So we can convert this that we have there to the following: the integral of the curl of E, or that dA, and that is equal to what we have on the right hand side, which is simply the same thing. No, wait, let's see. That's the curl, not dot product. The curl of E. The curl of E, right? We have that. And we also notice something else. That this is essentially an E dot dA. So this is actually supposed to be a volume. And dot V. Allow me to check again that the theorem so that I won't be mistaken with respect to what I have to say now in this next part. Okay. The divergence theorem is precisely this. So let me write it down so that I won't be mistaken in what's needed to be here. So let me check this out. This seems to be a little bit of a mistake here. Okay. So the divergence theorem then says that if we've got our E dot dA, we can actually write it in the following manner. The divergence of the electric field, right? And this is actually over a volume, d tau, but of course it's an integral. And everything on the other side must remain as is, which is 1 over E naught S prime d tau. Okay, I just need to confirm what the divergence theorem, indeed I was correct. Okay, so now we have this being our new part. We see something. We've got the integral and it's still over the surface S prime, S prime. What we should see about this integral is very specific, is that we are integrating over the same volume, d tau, and not only that, we've got the same integration or the same integrals. The integration is the same over the same surface and the same volume. which means that if these two are equal, it means the integrand or the elements which are being integrated or anything on the left-hand side, but with respect to not the integral itself, must also be equal. And as a result, we end up having that the curl or the divergence of the electric field is actually equal to the volume charge density over the permeability of free space. This is the divergence theorem, but in a more generalized sense. But of course, the integral form, as you can see, is the top one, and that there is the point form, but in terms of the more general term with respect to more electrons or more charges that are being integrated over. And this right here, ladies and gentlemen, this is Gauss's law for one single point. This is Gauss's law for a concentration or a volume of charges. And this is the derivation that is necessary to prove Gauss's law in free space. So hopefully that was helpful. And that's it. Thank you.